Okay. Now then, let me talk about power consumption, right? So now we will start. We are done with the sizing of logical gate, the most difficult part. So you will have a lot of exercise in the assignment and midterm and exam, and even your project, right? So in words, the simple power consumption of the logic gate is just like the simple inverter. We discussed already. It has the short circuit current, which the short circuit will be much less, but it has the most important thing is the switching power. But switching power depends on the activity, because sometimes you're not going to switch. For inverter, if you have a signal change, input signal change, output will change. But for the NAND gate, it's not always changing. And also signal can be correlated, A and B, right? So that activity will depend on that. And that it also may depend on the glitches and the stacking effect. Okay, so let's take a look. For example, what is the switching activity? It depends on the function, right? So it depends on the probability that you have a 0 and the probability that you have a 1. Then that is a switching probability, right? So it's also equal P0 times 1 over P0. So how often? Because if you have n input, you have to the power n possible output. So you have n0, 0 or n1, 1. Then that is the switching activity, right? Very confusing. Let's take an example. This is the NOR gate. Right? Can you tell me how many 1 are there in the output? How often do we get 1? I mean, yeah, let's do 1 first. How often do I get 1 in a NOR gate based on this table?
25%.
25%, 1 over 4. How often do we get P0?
75.
Thank you. Oh my God. 3 over 4, right? So what is the switching activity probability? It is only 3 over 4 times 1 over 4, which is 3 over 16. It's not really half or not even 1, right? So the power consumption is just CV squared times F1 to 0, okay? Which means this is just CV squared times 3 divided by 16. So for some gates, they actually are less active and they consume less power on average. Of course, our assumption is that the input not correlated, right? If you have a logic function, always give you either 0. When A is 0, it gives you B1. If A is 1, B is 0, then you basically see that it's always 0. You never switch. Your logic doesn't consume any power. Of course, this becomes a useless logic. You should have primed it already in the optimization process. So this is first thing. It depends on the logic gate type. Any questions? If no, then the problem of the logic of this type of multiple input logic gate is that it can consume extra power due to the glitch. Okay, so let's look at this. At the beginning, they are all 0. So what is the output of each gate before transition? This is NAND gate. So 0 times 1, 1, right? As output is 1. You start with 1, 1, 1, 1, 1, 1. They are all 1 at the beginning, and that is this 1. Before transition, they all 1. You use this one maybe for adder or something. Suddenly you decided to change everything to 1, the input. It becomes 1. Okay, you become some, what is the correct logic? If this is 1, 1, this one's supposed to go to 0. But then now this is 0, 1, so this one should be also 0. I mean, also 1, right? It should stay at 1. If this is 1, 1, then this one should go to 0. If this is 1, 0, then this one should stay at 1 eventually. Make sense? And if this is 1, then this is 0. Correct? That is the ideal case. But the problem is, this signal comes later. Look at this. When this one becomes 1, 1, it propagates, it makes this become 0. Okay, no problem. But now, this is 0. But this one, if it comes later, this is 0 also. Did I do something wrong? 1, 1 will give me 0. 0, 1 will give me 1. Yeah, so it starts with yeah, I go to the opposite. I'm sorry. They all transit at the same time. This one all go from 0 to 1 at the same time. But this one takes time to propagate, right? Let me say one more time. So when this one goes to 1, this is 1, right? So 1, 1 will give me 0, no problem, right? Now this one goes to 1, but this one takes time to go to 0 because it was at 1. Now if both of you are 1, what will I get? When both are 1 in the LAN gate, I will go to 0 first. I try to go to 0 because I see this one is 1 and 1. But then later, the evaluation tell me that actually my output is 0. I'm sorry. And then I found that this is 0 and 1. Then I decided to go to 1 again. So as a result, for example, this out2, it tried to go to 0. It has a glitch. During glitch, it is a transition. So I suppose that this one and this also have this problem. These two gates supposed not to transit, so it should not consume any power. But because of the way I lay out, I did not consider this intermediate transition. It consumes some useless power. Is this okay? So the reason there's a glitch is because of the delay in the critical path. Okay, so let me summarize because I confuse you. All this at the bottom go up at the same time because it might come from previous logic. But because of the way I implement this logic, I actually need to wait for this signal to propagate. So for example, when this one go up to 1 already, it is still in the O value of 1. I'm sorry, here. When this one go up to 1 already, it's still in the O value here. This one. When this one go up already, it's still in the O value of 1. Okay, so 1, 1 will try to make this one to 0. Until later, it find that, oh, actually I'm 0. Then you try to correct it or go back to 1. But in this process, I already lose some energy. Questions? Right. So just as example, you forgot why this one second last gate, right? what is the critical signal for it? The critical path, it is the out free, right? So the top one is the critical signal, okay? Now I also want to about the stacking effect. Stacking effect actually help us in the device, right? So if you look at the NMOS LAN gates, right, you have this. Let's say if this is 0, this is 0, this is A, this is B, the current leaking is less than inverter. So why is that? First of all, VTH1 is larger than VT0. Can someone tell me why? We just discussed it last time.
Body effect?
Yes. Because of the body effect. Okay. And if we just look at M2, this is M1, M2. In M2, we also need the leakage is proportional to VDS divided by KT over Q, right? But the most important thing is proportional to negative VDS. VDS is less, is smaller than in inverter, right? We can look at it this way, right? So that we actually have much less leakage. This is called stacking effect. Okay. So I'm done today. I'm too slow. Something happened. I don't know why I keep making mistake. But any questions? Sorry for confusing you. Any question? We can discuss more.